Okay. Well, nice to see everybody again. As always, there's like technical difficulty. I don't understand. I think the camera's just like slowly dying throughout the semester here. It seems to have reached its last legs here, but that's okay because you're supposed to go to class anyway, and plus you already did your last homework, so at this point it doesn't matter. Let's see here. In terms of course logistics and so on, your last homework was due yesterday, I believe. So I guess I look forward to receiving all of your homeworks on Friday, given how late days work, at least some large fraction of the class. But in any event, after that, you're free of homework. And all your remaining deliverables are the course project. So there's a write-up and a presentation. Thea posted a presentation sign up on the Piazza, so be sure to go on there. Essentially, the way this is going to work is you sign up for a time now, even if you don't have your slide deck ready, obviously. And then before you actually give your talk, put a link to a Google Slides in there, so that way we can just use a common laptop and not have to switch out. Those talks obviously will not be filmed. The presentations, I think we slotted, it's like 8 minutes plus 1 minute transition. Somebody asked about Q&A. We can do that during the minute of transition. Look, the way this works, for every minute we add to your individual talks, it adds 30 minutes to the class. So we have to be a little careful about that. That also means that I will pull you off of the front of the room should you reach that 8-minute mark. Okay? So practice. Our students never practice their presentations, but you can. And the good news is, if it was successful, you know how long that practice should take? 8 minutes. And if it didn't, then you learned something. Yeah? So might I suggest, for 8 minutes the day before, this is not a big ask, to practice your course presentation and just make sure it fits. And you're going to think that it fits before you practice your 8 minutes, and then you're practicing and realize it doesn't, because they never do. Okay? So this is my plea to all of you. Don't make me drag you off of the front of the room. I don't like doing that. I'm not a very good linebacker, and it's just a lot. Cool? Any questions about the project or logistics, anything else? And I posted on Piazza a few simplifications of the homework. The homework as it's written is correct, it's fine, but sort of annoying calculations, and I didn't feel like doing them in my office hours. So lucky for you, now they're extra credit on the homework. If you do them, that's fantastic. Okay. So, with that, we'll continue our technical discussion. I guess what's on the screen isn't 100% accurate. So we're going to wrap up our discussion of vector fields a little bit, and then we will start our discussion of optimal transport. It's a topic I know and love, so chances are it'll go long. So we'll probably start today and continue next time. But before that, I promised you guys a little bit of vector fields in machine learning. There are not very many pieces of chalk that are longer than a toenail. And in particular, there's one kind of interesting vector field design problem that's been quite popular in machine learning the last couple of years that I thought is worth mentioning to all of you, because it actually has some commonality with the graphics techniques, which is kind of fun. And moreover, I think if you see recent work on this problem, they're actually kind of merging together more and more, which is kind of fun. So in particular, I thought I'd give a really brief introduction to the following topic, which is continuous normalizing flows. Or CNFs for short. I'm guessing, because you guys are all grad students in the 21st century, that many of you are probably more familiar with this topic than I am, but I read through a survey paper and I thought, gosh, this looks like vector field design, and so why not? Let's cover a little bit of it. Just to give a quick idea of where vectors show up when they're not just two-dimensional. And in fact, this is, I think, one of many. I hate this chalk. Apparently Jonathan Reagan Kelly actually went out and bought the fancy Japanese chalk from the special mine that mathematicians like. You know this whole story? There's a company, they went bankrupt, and so everybody went and fought for it. So Jared K apparently has a big stash he's hiding from me. Okay, so in any event, basically all of this stuff is going to be based on, there's a really nice survey paper out there. It's by Papa Makarios. And hopefully I spelled that right. Yep. And colleagues. And this is in JMLR 2021. I really recommend taking a look at this survey. Like, some of these survey papers are just like excuses for people to get an extra publication and like just long lists of citations. But these folks actually thought through it. Like there's really nice kind of categorization of this research and mathematical language that at least spoke to me. I don't know if that maybe means it speaks to nobody else, but I found it to be like kind of interesting, insightful way to understand what's going on in this space, especially because with any popular machine learning topic, the problem is that like within 5 minutes, there's like 75 papers that are all different versions of one another, and it's hard to kind of cut through and categorize. Sorry. Why are you guys messaging me on Piazza while I give lecture? Okay, so, right, so basically continuous normalizing flows are techniques for dealing with probability measures. So recently, of course, some topics that are very popular in machine learning, computer vision, natural language processing, so on, are these generative models, right? Where you're essentially trying to, for example, randomly sample from the space of images, right? So like we have all these deep fake photographs that are just like images of humans and so on. And very abstractly, one way that you can kind of understand what's going on is that you have some probability distribution in a very high dimensional space. Right? Like for example, the space of all possible n by n images, and of course your probability distribution is very thinly peaked within that space. And there's sort of two different tasks, depending on what corner of machine learning you're in, that you might want to carry out. Right? One of them being sampling from that probability distribution, like GANs and, I don't know, diffusion models, whatever, are often used for this. The other being density estimation, right? Like if I'm given an image, how likely is it that I would observe that in the wild? Those are sort of the two kind of central problems that a lot of folks study in this kind of inference domain. So essentially these continuous normalizing flows, what we're trying to do is we want to parameterize probability distribution, and we'll call it P of X over RD. And so the idea here is that like, one of the annoying things here is just like, what is a reasonable space of probability measures? Right? Like for example, the one you probably learned about in stats class is just the set of Gaussians, but of course, the space of images is extremely non-Gaussian. and so we need some more flexible language to be able to kind of describe a bunch of distributions that we might encounter in the wild. And of course, there are many different models for how to do that, and if you've spent any time kind of reading through inference or Bayesian literature or anything else, you may have encountered a few. But here, essentially, the trick is going to be the following. We're going to think of our space of distributions as ones where we'll sample from something that's easy to sample from, and then we'll have like some deterministic process that takes me from the easily sampled but boring measure to the much more difficult sampled but interesting measure. Okay? So in particular, here's what we're going to do. We're going to say our random variable x, we're going to write x is equal to t phi of u, where u is sampled from some other distribution p psi of u. And so the way to think about this here is that there's two sets of learnable parameters here. One is psi and the other is phi. And the way to think about it is that like p psi is going to be, well, think of this as like somehow easy or simple or like easy to deal with. So like maybe p psi is just a Gaussian distribution, and psi is its mean and standard deviation. And then we're going to learn a transformation, which takes samples from the simple guy and then pushes them to a more interesting distribution. Okay, so that's the basic learning problem. So to draw kind of a picture of what this looks like, so maybe we have a distribution like this, which is p psi. By the way, I'm going to try and be consistent with my notation, but as we've seen, I'm terrible at that. So we're going to call this variable u. Maybe it's parameterized by like its mean and its width or something like that. By the way, I think in a lot of papers, the psi here is non-existent. Like this is sort of optional variable. And then we're going to learn a function. So like let's say that I have a bimodal distribution that I'm targeting, right? Then maybe I learn a t, which maps things, kind of clumps them to the left or to the right. So sampling from my distribution P here, and this is T phi, involves sampling from P psi and then using some procedure to warp that sample into the final target. Does that kind of high-level picture make sense? So this high-level one is an approach that's common not just to continuous normalizing flows or even normalizing flows, but just generically in probability. This is a totally reasonable thing to do to think of a random variable, sort of the image of a certain map. But essentially, the magic comes in choosing useful structures for this function t phi that are going to make it easy, or easy is a little strong, but like are going to give us useful formulas for either density estimation, sampling, or some combination thereof. Right? And the kind of cool thing is that this can be connected to, to vector field design. Yeah, and so already many of you probably, if you have any experience in this domain or related ones, might think of t phi as being some kind of neural network. I think would be the popular tool to use these days. But there become some questions with this procedure depending on how you use it. So for example, let's say t phi is just a generic network, or if you're not familiar with neural networks, it's like a generic function, right? Then let's say that I'm given a u, or an x rather, right? That's our x space downstairs. I could ask, like, what is the likelihood of x? Right? And how would I have to do that? Well, I'd have to invert my neural network to find the preimage of x up here, and then calculate a bunch of Jacobians and sum them all up. And as you can imagine, inverting a neural network is not a nice procedure, right? That's a difficult thing. And so a lot of engineering has gone into designing t phis that are at the very least invertible, maybe differentiable, or diffeomorphisms, so that they have these nice properties that I can work with later. Is that a high level kind of picture make some sense? Okay, fantastic. So again, our learnable parameters here, or optimization variables, if you don't want to call them machine learning, are going to be phi and psi, where psi determines what we'll call the base distribution, and phi determines the mapping. Okay? Cool. So there are a lot of useful properties to have here. And I think that the main one, let's see if I want to, for example, evaluate density functions here, is to at the very least have this function t be invertible, right? Like otherwise it's very hard to compute likelihood, because like the likelihood of ending here, ending a particular place, you have to find like 5 different preimages that it all could have come from, which is not so great. Yeah. So we're going to start to kind of articulate a few ansatz that are going to be useful for designing our function t here. So in particular, maybe we want t phi to be invertible. And moreover, we're going to use some formulas from calculus, like change of variable equation. So we'd like to have some derivatives at our disposal. So maybe in addition to this, I want that t phi and t phi inverse are differentiable. Okay. These 3 conditions together define a particular kind of object, right? This is sometimes called a diffeomorphism. Okay. And so essentially the trick here is rather than using a very generic neural network, for example, for t, we're going to choose one with these properties. We're going to like build it into the structure rather than like maybe adding a loss that kind of tries to make that happen or something like that. Okay? So why do we like these 2 properties? Well, together, so in this case, we can actually write down a likelihood function. Like we can just write down this function p of x in closed form. And it takes a really nice form, which is the following. We can say, okay, well, p of x is equal to p psi of u, where we're going to think of u as the pre-image of x, times the determinant of j t phi of u inverse. Okay? I'll reuse the bad writing on the board here, where u is going to be just t phi inverse of x. In general, whenever you see x and u, we'll assume that they kind of go together. Does that make sense? So does this formula look familiar? This is the integral change of variables formula, right? Like this is just how probability distributions warp around when they're under a map, right? So like my map is like stretching stuff out. So it's good to do a sanity check here. So if you think about it, if a map is stretching stuff out, then you would expect likelihoods to decrease because you're taking the same kind of interval and smearing it over a larger amount of space. And so that kind of explains that -1. That make sense? Cool. All right, so this is called the change of variables formula. By the way, just for convenience, here the Jacobian j t phi is nothing more than the matrix of d t phi I b u j index over I, j, which we're going to think of as R, D, I. Notice that, like, for this formula to make sense, we need the output and the input of T to be the same dimensionality, or we can't invert matrices. There are some probability models where that's not the case. I mean, you could imagine sampling like a high-dimensional object and squashing it in a low-dimensional space, or actually the other way around. Like maybe you think your distribution is like peaked in its surface in 3D, so you sample a 2D thing and map it forward, but then densities don't make any sense, right? You have to be a little careful. Okay, so far I haven't described for you continuous normalizing flow. In particular, like the continuous aspect isn't really there. But this is sort of the general name of the game in this normalizing flow literature, is to parameterize a set of T's that's somehow easy to work with and learn. And here, notice that we can both do sampling and density estimation, right? Because we can do sampling by just drawing samples from p psi and then pushing forward through T. And we can compute density by kind of going backward through T and evaluating this formula, right? And this formula is ugly, but at the end of the day, it's just autodiff, right? This is like what PyTorch is made to do. So why do we like this kind of stuff? So there are any number of problems that benefit from this kind of parameterization. Here's a very simple one. So maybe I want to solve a maximum likelihood estimation problem. So let's say that I'm given a bunch of photographs, and I want to make like a new deepfake photograph generation machine, right? So abstractly, here's one model for how we might do that. Suppose we have a bunch of samples like x1 through xn, and they're all drawn from some unknown p star of x, right? So I think of this as our distribution of all possible photographs, and here are some samples that I drew from. Make sense so far? So a very typical thing would be to try and find this p that kind of fits, that like looks like this p star, where the evidence that we have is based on these samples here, right? And so it turns out this is equivalent to maximum likelihood estimation. So here's one way to write a kind of reasonable loss here, maybe of phi and psi, would be to just evaluate the KL divergence between p star, which conveniently you guys all know what KL is because you finished your homework, and p of x here. So in other words, like, p is a function of phi and psi. I have, my p star is the thing that I really want. I have this thing I'm trying to optimize for, and KL is some weird notion of distance. Remember that it kind of looks, like KL of p q roughly looks like the integral of p x log p x over q of x, like that. And this is some notion of similarity between probability measures. Okay? So, incidentally, KL is not symmetric, and oftentimes we just kind of choose the ordering of the inputs that makes this problem convenient. I would say that, like, if you go talk to a Bayesian, they'll give you all kinds of, like, hot air of, like, why they, this guy should be the one, the first one, and that one's the second. But I think the reality is, 2/3 of the time you put it in the one that makes the algebra work, and if it doesn't, you go back and you swap. And then you come up with more high-level argument for why that was really the right one the whole time. In any event, but don't tell Tamara I said that. Right, so in any event, this particular ordering works quite well. So in particular, we can use kind of a clever trick, which is as follows. So the log of a fraction is the difference of the logs. Hopefully you all remember that, also from your homework. If not, you might want to revisit your homework. So this is, of course, p of x log p of x minus the integral p of x log q of x. Okay? So what is the variable in our problem? It's p, right? That's the unknown. Oh no, shoot, I have swapped. I've done a terrible thing. I'm sorry. This p and that p are different. Oh god. Here's what we're going to do. We're going to put bars on all these p's. Okay. And the q's, just for good measure. Have I lost you? Okay, good. All right, so the variable in our optimization problem is p, which is the second argument of KL, which in this expression is q. Is everybody cool with this? You should ask a question if you're not. I'm sorry, that's my bad. I knew this was going to happen. It's even in my notes with a little star next to it saying don't do this. And I did. Okay, so now my variable is q. I expand this expression here. Does this first term matter at all for optimizing for Q? No, right? Because my variable is here, right? This is the second input to KL. Remember, because it's that one. I'm so sorry with the P's and the Q's. Okay? So this like weird thing happens to look like entropy, which is cool. It's very deep, and we can think about it later. Is totally irrelevant for our particular problem. Moreover, what is this thing? If you think about it, so it's the integral of log Q against Px. So this is just fancy notation for the expectation over P bar of log Q bar. Okay? Isn't that neat? I think that's neat. Okay, so I'm going to erase this because it's stressing me out, and we're going to continue the line above it. Okay? All right, so okay, so we've got this thing, and essentially what I've argued for you with horrible, shameful notation, you know, people that normally teach this stuff, I don't know, Polina Golan would be very upset at me for what I've done. My tenure case is ruined, but in the meantime, what we've argued is that this thing is really some constant minus the expectation of x drawn from P star of log P, where this thing is really like, maybe you think of it as like a function of phi on its side. There's a gas leak at Kendall Square, you should go. Okay. Does everybody agree that that's sort of what we've argued so far? This is just like slick notation. Right, so at the end of the day, what am I going to do? Well, conveniently for me, remember, like, what is an expectation? It's like you randomly draw a variable from a distribution, and then you evaluate. And so this thing is roughly equal to constant minus 1 over the number of samples, the sum over the i's here of log p xi given phi and psi, right? And of course, you know, in reality, we just can remove that in our optimization problem. Well, now we're cooking with gas because like we have some expression for the log density, or at least the density here, right? We can certainly take the log. So what is this thing? Well, this is the constant minus the expectation of, well, so we've got sort of the p psi and the determinant here. And since they're multiplied together, you know, we're taking the log, so you really get the sum, right? So this is the log p psi of t phi inverse of x. And then we're going to have a plus, because there's an inverted, the expectation over x again of the log absolute value of determinant. I'll just write j because I'm running out of space. Okay, but we're just borrowing this expression here. Okay, so what did we just do here? We said like I have a bunch of images that are sampled from my data set, and I would like the P, which is closest to my data generating distribution. So a reasonable model for doing that is to minimize KL, or equivalent to kind of maximize the sum of the log likelihoods over the set of samples that I have. And the convenient thing here is that what are the ingredients I need for log likelihood? It's essentially mapping stuff backward and evaluating P, which we know. This is like the density of a Gaussian, for example. And computing the determinant, which we're going to see is not so bad as long as we choose T in a very, very careful way. So this is an example kind of application. You can see the kind of ingredients, how they get mixed together here. Any questions so far? Kind of rushing through this stuff. I know there's a lot of symbols moving around. Cool. I know this is like old hat for those of you who do, you know, generative modeling, but if you haven't, then this language is it's tricky to think about. Okay. So now let's learn about continuous normalizing flows. Maybe we'll keep this picture here. I don't think the MLE matters quite so much, so we'll just keep moving. Can I fit it onto this board? I totally can. Okay, so now let's actually think about the CNF model. CNF also means something in computer science theory, right? Isn't it? Okay, normal. Yeah, I remember that from 2007. Oh boy. Okay, so remember, like we can choose whatever form we want for T. Neural network just by itself if we don't put some careful structure in there, is not so great because we need to be able to invert it. There are lots of people out there who have worked on design of invertible neural networks, including things they call normalizing flows that are just not continuous. But they're actually a bit tricky to design. But there's a really clever trick here that's directly related to what we've done in this course, which is the following. What we're going to learn is basically an ordinary differential equation, or vector field, that flows from one distribution into the other. So here's what we're going to do. We're going to say we have dz dt is equal to g phi of, I wish this person had erased a little bit better. Of t zt, like that, where we'll say that u is equal to z at t naught, and x is equal to z at t1. Okay, so essentially we're going to use like a neural network, or really whatever function you want, to parameterize this function g, which inputs a time in a variable and outputs a vector. It doesn't output a value. And so here's the kind of picture that you have in mind. Remember, like in our kind of example from before, we have this Gaussian, and we're like maybe flowing it into this bimodal distribution. Then what g is going to do is like learn this like vector field, kind of like that. Right, we're just taking samples, and if you look at the flow lines of this thing, are like kind of flowing them along curves that lead to your final sample. Does that make sense, like what the model is here? So there are advantages and disadvantages to this particular model. For one thing, one fun fact that we actually kind of covered in our discussion of vector fields that might have gone past quickly. If I take generically a vector field on Rn, so like Euclidean space, and I flow all of Euclidean space along that vector field for like a fixed amount of time, like 0.7 seconds, then I generate a map, right, where for every point in Euclidean space, I say, where did that point go after flowing for 0.7 seconds? And under pretty weak assumptions, that map is a diffeomorphism. It's differentiable and invertible. And notice that's exactly the assumption that we wanted when we started here. And that's, I think, largely part of the motivation for using differential equations to define these maps, is that you get some of these nice properties for free. And in fact, actually computing the map and its inverse, we'll see, are equally easy or hard, depending on how you think about it. So in particular, we have some ODE integration formulas as follows. So in particular, let's say that I want x, which of course is zt1. Well, we have dz dt. So what do we do? We just integrate both sides. Huh? So how do I get x? Well, this is nothing more than u plus the integral from t naught to t1 of g phi of t zt dt, like that. And of course, this is not a thing that we can do in closed form if G is a neural network. It could be very complicated, differential equation. But we've implemented many, even in this course, like you implemented forward and backward Euler on one of your homeworks. That's exactly what you can do here, right? Like G is a little vector field, and I can just step along it. So what do I want to do if I want to sample from my distribution? Well, I draw a U from my easy to sample distribution, and now I just step along my vector field. For instance, using forward Euler or RK3 if you want to be fancy. And what comes out is a sample from the final thing. Isn't that cool? Moreover, let's say I want to do the opposite of that. Like I want the pre-image. How am I going to do that? I heard like a little grunt. Yeah, yes?
I can integrate in the other direction.
Yeah, that's right. I can just flip the integral backward, right? I mean, u is equal to z t naught equal to x plus the integral. We have to be a little careful. I guess t1 to t naught. I guess we're used to thinking of that as just being a minus, but whatever. Again, of this thing. Yeah. I'm sorry, I'm like getting myself all confused with this sign. dt. Actually, let's just do. I think it should actually be that. Okay. But basically, you just flip your vector field backward and flow along the other direction, and then you get back from u's, from x's, you can get back to u's. Okay. I'm going to get this sign wrong here, but
Yeah, it should be plus.
should it be plus?
I think switching the t.
Oh, yeah, I'm sorry. This, if you think of that as that, I think this is a more natural way to think about this problem, but it is. Anyway, signs are annoying. I'm sure if you were sat in front of your computer, you'd figure it out. This is one of those ones that's annoying to get right on the board and very easy to detect when it's wrong in your code. Okay, so that's great. So once I learn this G5 function here, I can sample from my probability distribution pretty easily. And one kind of interesting thing here is that these are sort of equal complexity. There's something very democratic about continuous normalizing flow, which is different than a lot of these models. For example, like evaluating a neural network forward is very easy. Evaluating it backward, like inverting it, is very hard, like usually not possible. Right? Incidentally, if you're careful to track credit for these different ideas, this one was a very popular research paper that was neural ODE, which from you guys' perspective is probably a classical result, but it kind of several years old. The original idea was just to learn an ODE. They weren't concerned with density estimation, but just other problems. Yeah?
So GT5 is also a neural network now.
That's right. In fact, it is the neural network.
And we have to evaluate it at each step of our
Yes.
order or whatever.
Yeah. So it's sort of expensive, right? Like to do the forward model. And in fact, typically I say typically, but I'm not sure this is actually true in practice. One advantage here, and something that was considered in this neural ODE paper, is that you could use adaptive integration for this formula here. Like you could take T to be big if you think T is kind of low frequency, and maybe you change that throughout your training or based on your samples. I'm told in practice a lot of people don't bother. But what that can mean is that if you take really tiny time steps, you're evaluating this thing a bunch. One kind of interesting thing is you don't actually have to differentiate through it necessarily. There's sort of two different ways if you need to backpropagate through this that you could do so. The first would be to just implement forward Euler in PyTorch and then just keep around that whole computational chain and differentiate through it. There's a second one, which is actually borrowed from like the Aero-Astro literature. They call it adjoint method. And I'll refer you to the neural ODE paper to kind of justify where they kind of show like I can integrate this ODE forward but not remember my path, and then integrate some other formula backward along a different path and get the derivative, which is kind of nice if you take a lot of steps. Again, each of these things induces some error, so you have to be a little careful, like then your gradients are a little inaccurate. And moreover, your gradient doesn't even agree with the forward paths that you discretized, right? So there's definitely some advantages and disadvantages there. Okay, so we can draw samples, we can invert samples, we're almost there. We need density estimates in order to evaluate some of the formulas we had. And conveniently, that's actually not so hard either, it turns out. So there's a really handy little ODE that says the following, that actually the d log of p, so if we think of p z of t like that as the density of the random variable, dt, this is actually equal to minus the trace of Jacobian of g phi. Yeah. Like that. Now, if you think about it, what is the trace of Jacobian? It's basically like divergence. And so this formula actually makes a lot of sense, right? Like what it's saying is that somehow when your probability is like spreading out, right? So like you have positive divergence, then your density decreases because probability is spreading out, right? That's like roughly what this formula is saying. Again, I think signs are really important to think about. This is kind of nice because like now, okay, so what do? Like I evaluate this integral forward in time. So now I get, p of zt, at least at like some discrete set of t's, and now I can kind of secondarily solve this ODE at least at the same set of t's using this formula here. There's one annoyance, which is that you have to compute the entire Jacobian of your field, which in many cases is an annoying thing to do, especially if you're in like very high dimension. So what was proposed back in the day was kind of a clever trick, which I thought I'd write down just because it is kind of a clever little math idea, which is for trace estimation. I don't know if have you guys encountered this little idea before? It's a fun one, and traces show up all over the place, so I think it's worth covering. So, I'm going to write something really profound, which is that the trace, I'm just going to write j because I'm too lazy. This is equal to the trace of j times the identity matrix. I think we can all agree, hopefully. Okay. So it turns out there's a lot of useful formulas for the identity matrix. And one of them is follows. So let's say that I randomly draw a vector in Rn from a Gaussian distribution with like mean 0 and covariance 1, or covariance I. Remember what the definition of covariance is. So this is equal to minus the trace of Jacobian times the expectation over our variable, what we call it W, of W transpose. Actually, the definition of covariance, assuming mean 0. So like, I'm just thinking of W as a Gaussian mean 0 random variable. I can draw these easily on my computer. Okay? So I haven't written anything too profound yet. I'm just writing identity matrix in a lot of different fashion. Okay, so conveniently for us, everything here is linear, right? Expectation linear, so I can pull it out. So this thing is equal to the expectation over W of minus the trace of JWW transpose. But remember that traces can cycle around. So this is minus the trace of W transpose JW, like that. This is a 1-by-1 matrix. Do you see that? So in reality, this is just minus the expectation over W of W transpose JW, and I'm going to kind of parenthesize it like that. Okay, so this is called the Hutchinson trace of HUTCHINSON. I know that's legible to all of you. This is called the Hutchinson trace estimator. You can Google it later, but basically here's the trick. So like evaluating J, so let's say that I'm like inferring a probability distribution on like 1500 dimensional space, right? Then J would be 1500 by 1500, which is not so great. Yeah, so then you have to do backprop for each element of those. I mean, at least in principle. Like obviously PyTorch knows how to do that in smart ways. But that's expensive. I mean, it's like 1500 squared times more than the original derivative of your computer. So instead, in the Hutchinson trace estimator, you have this funny formula for the trace of a matrix where you randomly draw a Gaussian random variable, and then you evaluate this W transpose JW, where J is the thing whose trace you're trying to compute. And here's the sneaky thing. If I look at this product JW, what is this thing? Is a directional derivative, right? So now, instead of having to compute n squared things, I only have to compute n of them. I just take the derivative in one direction. And you can even implement this in like PyTorch in a careful fashion so that you really just get a linear number of derivatives back out. So you don't end up with a quadratic number of variables you have to compute, just a linear one. Can anybody think of the problems with formulas like this? Yeah?
How many values we need to draw?
That's right. So like this is an unbiased estimator, meaning that like in principle I don't have to draw one W, and then at least on average this thing will average out to the right trace. But of course, if I use that for my machine learning system, I'm gonna have very high variance in the variable that I actually compute. So probably you want to like draw 10 W's or something and average the result. But at some point you draw enough of them, you might as well have just computed the original thing, right? So this trace estimation thing, I'm told, is quite tricky. There's some tricks to make it a little better. This trick works for any mean 0, variance 1 random variable. Apparently Rademacher distribution does slightly better here. That's like a +1, -1 distribution. But that's all mythology. I think there's relatively little math there. Okay, so why do we go through all this? Like, I was looking for like the interesting vector field design problems that show up in high-dimensional machine learning, since that's part of the kind of promise in this class. And actually, the kind of interesting thing that happens in this literature, which is cool, and I encourage you all to now take a look at this survey that I mentioned all the way at the beginning of our first slide, or board, or whatever. Essentially, this is a wildly under-constrained problem. So in particular, there are a lot of ways to take this distribution, like this Gaussian, and map it onto this bimodal thing. Like it could all move very quickly and then stay. It can move slowly. It can follow a curved path and wiggle back and forth and then land on the right distribution, whatever. Right? Like you can imagine this is very under-constrained. There are a lot of G's that, from the perspective of this objective function here, are equally good. Because this function doesn't care about the path. It just cares about the final result. The same way, like if I said, like, come up with a way to get from this corner of the room to the other, and in 10 seconds you could like sprint, or you could take a direct path and walk more slowly, and either one of those is fine for my yardstick, right, as long as you get there. Yeah, Rishem.
I'm a bit confused about the streak as a trace.
Because like the trace is just the sum of the diagonal, right? So like to calculate the trace, we already need only n elements. We don't need the full matrix.
That's right, but but they're not quite directional derivatives. They're like the diagonal of your matrix, which turns out to be a harder thing to evaluate. Yeah, that's what I'm told. But I don't know. You guys are the experts. Right. So in any event, this function g here, like there's probably a lot of different neural networks that perform equally well, but they may be more or less stable. Like for instance, some of them might not do as well when I approximate this integral here. Maybe some of them somehow take paths that are going to be hard to approximate and so on. And so if you read through this literature, a really funny thing happens, which is people start adding objective terms that look at the vector field design of G as a vector field, which is super cool. So to give a few examples here, one ansatz you can put on G is maybe that G is actually equal to the gradient of some function f, where f is like a scalar valued neural network, and then G is the gradient of this thing. In the language of our previous lecture now, remember the Hodge decomposition, what does that tell us about G in this case? Yeah?
Curl-free?
It is a curl-free vector field, right? So now the particles from G can no longer take like weird windy paths. On the other hand, they can compress quite a bit, which can be a problem because, of course, if your sample is compressed and then you want to invert your neural network, then like there's a lot of instability in that numerical integration that happens. Fun fact, it's actually sufficient to constrain f to be a convex function, and then that will lead us to optimal transport, which we'll talk about momentarily. This is the Monge formula. Other people have done the opposite of this. Maybe you actually penalize the divergence of f because you want it to kind of look like a rigid motion, and somehow that can make for more stability in the numerical integrator. This is one of these literatures where there's like any idea you could think of, somebody has probably proposed some small regularizer and published it. There are even some really wild ones out there if you read this survey. One of my favorites, which I can't decide if I hate it. I don't know. I got a new mattress the other day and I feel the same way. Like I woke up in the morning and I was like, I feel okay, but I think I hate it. Like this integral here, you have to approximate, right? Like you use like Euler method or whatever. One of the papers out there says, I'm going to add a regularizer on my vector field that looks at the difference between Euler method and some other higher order integrator, and says that a good vector field, since I might as well choose, I can choose any G I want so long as it accomplishes my goal, I might as well choose one that's easy to integrate, meaning the error of Euler's method is low. And so they like compute like the higher order derivatives of G so that you can kind of look at the next term in the Taylor series for your ODE integration, and they minimize that thing, which is just wild. I mean, like it's impossible to think about in terms of like smooth math, but it makes perfect sense from a perspective of how they're using it. So in any event, this is the tip of a fun little iceberg. This is a kind of new emerging topic in machine learning, relatively speaking. I would say the last like 5 years. But really, all of the vector field design topics that we've been talking about for surfaces directly apply here. And in fact, there's some overlap. Like my student Paul borrowed some of these tools and used them for computer animation. So he said, like, great, if I've got an animated character, I could use vector fields to kind of guide their motion, and then I could add regularizers on G to kind of make for like interesting, like rigid things or swirly shapes or whatever. Right? So it's kind of interesting. There's this like feedback loop between these kind of two different distance spaces. Okay, so that concludes our discussion of vector fields. Any questions? You've been asking questions the whole way. But I think this is a fun topic. And really, again, this survey from Papa Macarius and company is really worth reading. Like, there are a few surveys in this space, but this one was like really tidy. I can't speak to whether it's the most comprehensive or if they're like shaming themselves by not giving due credit to the right research paper, or like the usual academia stuff that we worry about, but just from an expository perspective, it's nice. Okay, so as promised, I'm talking too much. So this class, we've now got a good, what do they call this, like a fence post problem between lecture topics and class periods, but we'll get halfway through this topic here and we'll continue next time. So the next topic in 68410 is going to be an area that is close to my heart, and also one that is linked to these probability inference problems. So this is actually a nice transition. In particular, when we were talking about maximum likelihood estimation, we used this very particular choice of distance metrics, this KL thing. And really, it was for convenience, right? Like we just did all this algebra, we ended up with a formulation that kind of plays well with this normalizing flow machinery. It turns out it also plays well with a lot of other algorithms and models. But we'll see that there's some drawbacks, that this is maybe not the best choice of divergence for certain tasks, and that maybe adding a little bit more geometry in this probability language can be a useful thing. And that sort of motivates this area of optimal transport. This has this history, oh gosh, back in the 17 and 1800s. Monge kind of originally proposed these problems, but then couldn't solve them and kind of put them aside. Then in the 1960s, Kantorovich got a Nobel Prize for studying these problems from very different perspective, and these days mathematicians study them in very high dimension and with application not just in moving Russian troops around, which is a weird thing to think about today, but also in very high dimensional probability measures. So that's our motivation here. End of slideshow, exit. Oops. Oh, I see, we're at the end. Sorry. Okay. So, unfortunately, if I close PowerPoint, then the lecture recording will stop. So we're just going to awkwardly page through about 100 slides. Okay, so I really should put a marker on the final slide so this doesn't happen. Next time. Okay, now we're at the beginning. So here's our basic motivation. So oftentimes, let's say that we are doing statistical analysis, bless you, and we want to compare histograms. So I walk into a classroom and I collect the height of all the students in the class, right? And thanks to central limit theorem, whatever else, if I have enough students in this classroom, probably not this classroom because your last homework was due and I'm never going to see half of you again. I have enough students here, I bin them all, I get their heights. Then I get some probability distribution, that roughly, I was going to put 0 in the middle, but that actually doesn't make any sense. It looks something like that, yeah? And so I bin all of these things and I get some histogram that looks like what's on the screen here. And now, maybe I go to a classroom where people are taller, I don't know, Netherlands, I feel like they're tall. I collect their heights, and they're biased somewhere over here, right? So there's, 3 feet, there's 10 feet. And now I want to draw a conclusion like people in this classroom and people in that classroom are significantly different from one another. Yep. So in practice, if I'm applying my undergrad stats prowess to this problem, what do? I take all these people, I divide them into ranges, and I kind of bin them, and I get histograms like what's on the screen here. And then I compute, I want to know how similar or different these things are. So maybe I use some measure I could do the L1, where I just sum like that, Pi minus Qi, right? So I just look at all my bins, and I say for people between 5 feet and 5'5", here's the difference, and I'm just going to sum them all together. Or if I'm feeling fancy, I say, but I just did my last homework. I want to do some kind of information theory style loss. So I do, Pi log Pi over Qi. And these are totally reasonable notions of divergence. And indeed, if I have relatively few bins, they'll detect, are these classrooms from the same place or are they from somewhere different, right? Do I get distance 0 or not? But then I say, I'm a clever student and I want a more accurate computation. And how can I do accuracy? Well, I noticed that my histogram here has maybe 10 bins. And so how can I make this accurate? Well, I could make, 20 bins. I could divide all my bins in half. Now that the histogram gets shorter, but I've somehow been, I've got more resolution on my calculation. The number of students I have in the classroom has not changed. So on average, the number of students per bin has just shrunk by 2. Does that make sense? And I do my calculation for a while, I get happier. Obviously, if I have 1 bin in my distribution, it's not a very informative measure here. As I start adding more, I get something kind of interesting. But then eventually, I say well, if I want a really accurate calculation, I should just have 5 billion bins in my probability histogram. I should just have all the bins in the world, yeah? As many as there are bits on my laptop. But there's still only 22 students in the classroom. So what does my histogram look like in that case? I mean, it looks like this, right? You've got a bunch of 1 students sitting in their own bin. And so if we think about this sum here, what's it likely to be? Well, if I get a different classroom, I don't only have one color of chalk, but maybe I'll draw them as circular. like that, the likelihood of two different students ending up in the same bin goes to 0. So for any two classrooms, this measurement will be the same thing, which is roughly n. So is that an informative measure? No. So there's like some really weird thing that happens in statistics. You have like, here's your number of bins, here's, I don't know, usefulness. For a while, the usefulness is 0. If you have one bin, obviously you can't distinguish between classrooms. Then I add some more bins and it gets better. And then eventually, everybody just ends up in their own place, and my measurement gets worse again. And that's true for a lot of these kinds of histogram style calculation. So in optimal transport, the idea here is that we have one piece of information that we haven't really leveraged yet, which is the fact that there's an x-axis here, right? Like the horizontal axis here, ironically, is like the height of your student. And somehow, like, these two students are much more similar to these two students. But yet, this calculation does not take that into account, right? I could permute them all around, and I get the same result. And so that's sort of the high-level motivation for why, like, a lot of times these statistical divergences just don't cut it. For like distributions that don't look kind of wide and chunky and Gaussian, maybe if you have some notion of geometry that's attached to your probability measure, you can do a little better. Yeah. And here, notice there is a notion of geometry, which is the height of the student, right? That has a distance metric on it. Does that motivation kind of make some sense? Obviously, I'm taking to an extreme, but that's the sort of perspective here. And so optimal transport is a fun thing to cover in this geometry course because it's essentially a way to compare probability measures from a geometric perspective. It has this history, there's a long history of very famous mathematicians that have worked on this stuff. It started out with Momsch and Kantorovich. There's like, 200 years between these two guys. The time axis here kind of squashes as we go to the right. And eventually there are many other landmarks. The early linear programming people actually had a lot to say in this theory, including a lot at MIT. Wasserstein is kind of an interesting one because his name is all over this theory, but actually I think it's sort of considered that like his contribution to this space is relatively small. His name is just attached to a thing that ended up being very common. He's also a professor in Penn State, I think, and he has this little webpage of all these people that use his name and think that he's like a classical dead old guy. I'm on there. And then there's these folks who are all alive and active in this space, including Villani, who's a Fields medalist in this domain, and at least I think formerly now French politician, right? He was a representative for that neighborhood with the École Polytechnique in Paris, and I think his term recently ended. I can't say that I have kept track of French politics very closely. Okay, so our plan for today to talk about optimal transport, we'll talk about the construction of this, and this is one of these mathematical theories where there's like one kind of basic construction and then like a million equivalent formulations that look completely different from one another. So we'll talk a tiny bit about that. Then we'll talk a bit about the applications and some of the computation people do in this domain, both in low dimension and in high dimension. Okay. This is one of these areas that there's a lot of stuff out there. For your reading assignment in this course, you'll find no shortage of tutorials and research papers of people that work on this. They tend to be French. Here are a few pointers to textbooks, including some surveys of my own. This is unlike some of the topics we covered in the space. This is one that we know very well. I didn't feel like I had to prepare notes for this lecture. Okay, so right. So let's talk about our introduction here, and see if we can go from this intuition that like something is a little wrong with histograms to a better construction. Okay, that's our goal here. And essentially, the kind of identification that optimal transport does is to link together probability and geometry. And already, I think when we talk about probability measures, we do this intuitively, even if we don't call it out for what it is. So for instance, if we talk about Gaussian distribution, like a normal distribution centered at a particular average, somehow you can think of this as like some kind of fuzzy encoding of a point that's maybe located at this location here. And of course, if I refine this distribution about its mean, then it approaches a very well-known probability measure called a delta function, which is just like really thinly peaked right at one place. This is like a very confident location. So in some sense, the transport language is going to allow us to encode a bunch of classical geometry computation as a special case. Like we can compute distances between points by inputting delta functions into transport distances, but it also allows for other stuff, like the superposition of two things. Okay. Now, if you look at the computation that we did on the board here, we'll see that like a lot of the computations that I'm like kind of criticizing here that go wrong, all follow a very similar pattern. So I have two, histograms or density functions. Either one's kind of okay here. P1 and P2. And a lot of the things that you learn about in stats class for comparing these things, maybe they just like subtract and then square and integrate, right? And, or if you're fancy, you do KL, but really, essentially it's just iterating over X and then doing some computation that locally compares and summing. Does that make sense? And so from perspective of this calculation, like we've argued, a lot of the distances that we've computed here are not terribly interesting. One way to understand that is that essentially what we're measuring is overlap, right? Like this is kind of like comparing in the vertical direction how similar the blue and the red functions are. And in particular, you can do one experiment, which is exactly what I show you on the board here, or on the screen rather, where maybe you fix one probability measure, like the blue guy here, and you take the red one and you look at its mean, and you kind of scoot it around, to different locations, and look at the divergence as a function of mean, right? So like, maybe if the blue guy is mean 0, so we'll just say blue like that. And now we're going to look at, oh boy, this was a bad labeling of axes. Sorry. We're going to look at the following, which is the distance between the mean of the blue and the mean of the red, okay? Like that. And the vertical axis here is going to be, for example, KL divergence or L1. I'm sorry, I shouldn't have labeled the vertical thing. Well, what's going to end up happening? Well, obviously, distance here is small when they're right on top of each other for any of these measures. And as they start displacing, that distance will increase, right? But if I measure KL, what's going to happen is it's going to level off. Because eventually they just don't overlap, right? And so once the sort of main body of this Gaussian distribution is just like not on top of each other anymore, the distance is very small. That make sense? Whereas what we'll see in optimal transport is that you get something that just looks like a straight line. The farther you move stuff, the higher the distance gets. Now, why is this important? Like, if you think back, for example, to all these calculations we were just doing with normalizing flows, what do we end up doing a lot of times? We're like computing derivatives of these distances. Right? We're kind of saying like, how can we change our parameters phi and psi to make our current probability measure better? Well, here's a kind of typical issue that can happen, which is, let's say I'm trying to learn how to produce my deepfake photographs, and here's like the space of photos. So this is our probability distribution that we wanted. And now I initialize my neural network. And when I initialize, of course, it's not doing anything at all. So it's like generating noise, right? So probably like, here's what my initial guess is, right? What I'd like, when I see the gradient of my neural network parameters, is to do that. But in reality, the gradient is often just 0. Because it just says, oh, like there's no way to make this thing shorter and just have it kind of reappear over there, which is what KL divergence measures. Yeah. Okay. So rather than integrating some difference between like the two measures here, optimal transport takes a very different perspective, which is the following. Unsurprisingly, given the name, what it's doing is moving mass around. So we kind of switch to a new analogy here, where we think of these red and blue functions as like piles of snow. And then you're going to solve an optimization problem, which is to say, how much work does it take for me to scoop up the red guy, walk over to the blue guy, and drop it back down? Right? And this is going to end up being a linear program, right? And of course, there are many ways that I could do that, right? Like, if I've got a bunch of snow in my front yard, and like Leticia in her yard is like, for whatever reason, it's in the shade, she doesn't get snow, and I'm like, okay, so like I want to move my snow onto her lawn. Right, there are many ways that I could do that. I could scoop it up. I could like drive around Boston, like make a detour. Stop at, I don't know, what's the famous Boston landmark? City Hall, and then drive to Leticia's house. And that's a lot of work. Or I could like take a direct path, like scoop it up and walk right over there. Obviously, those are different amounts of work, right? Like as I travel, but I can never go to 0, right? Like there's some amount of work that is intrinsic to the difference between these configurations, which is the minimal amount it takes for me to displace one on top of the other. And that is exactly the transport distance, right? So to put it differently, like even the laziest shoveler has to do some work. Conveniently, when I was preparing these slides, this is my front yard. This is not this year, obviously. And maybe I have the configuration of snow on my front steps. I have where I want it to go. And then, of course, before I shovel anything, as a mathematician, I get out my linear programming tool, and I start kind of figuring out where I should scoop up my snow and where I should drop it. And sadly for me, there is a positive amount of work that I have to do there. So, this is the mathematical notion that we're after. How do we scoop up one distribution and drop it onto the other? That makes sense? So, what do we need to do? We need to define our enemy here, our variable, and then our optimization objective. Bless you. So, we have, here's going to be our variable. We'll call this a function pi of xy. This is the amount of snow that I can pick up at point x and drop at point y. Okay? And pi has to satisfy 3 constraints. First of all, I can't move negative amounts of snow. Bless you. Okay. Beyond that, if I can move negative amounts of snow, then I could be very efficient with how I move it around. Yeah. In fact, the snow would be moving me. Okay. So, but that aside, I need to satisfy 2 constraints. Namely, let's say that rho naught is the configuration of snow on my front yard. Then what I say is for every point x on my front yard, if I look at all the destinations y that it could go to and I integrate over all of them, it has to equal the amount of stuff that's piled up at x. That's the second constraint. And similarly, for every point on Leticia's yard, y, if I look at all of the points on my yard that get delivered to that and I integrate, then it should equal where I want, how much I want to go at that point y. That makes sense? So, this has a name. This set of functions pi that satisfy these 3 constraints. By the way, usually we think of them as measures rather than functions, but we're not going to worry about that distinction in today's lecture. These are called transport plans or measure couplings for obvious reasons, right? This is like literally giving me instructions on like where to put stuff. That makes sense? Okay, so that leads us to an optimization problem, which is as follows. This is called the Kantorovich problem. My Russian brother is not very good. I have no idea how to actually pronounce this name. We can ask our students later. But essentially, what it's trying to do is the following. We're going to think of c of x comma y generically as the amount of cost it takes to move stuff from x to y. So maybe this is distance, or distance squared. We'll see both of those are valuable. And essentially what it's saying is over all possible transport plans, I want the one that minimizes the amount of work, which is equal to mass times like distance traveled. That makes sense? So this is our optimization problem. This is a very generic form. Usually c of x comma y is the distance from x to y to some pth power. But not always. It turns out that like a lot of the analysis just applies in this generic case. Which is good, because I mean you can imagine some like weird logistics problems where like c is weird. Like maybe like once I have to get into my minivan, then suddenly the cost is a lot higher than walking or vice versa or something like that. Or sometimes actually economists do study weird c's, like distance to a negative power, like economy of scale. Like if I take a lot of stuff a far distance, maybe that's better than taking little stuff and distributing it every which way. So there are a lot of variations of this. Yeah, Zoe.
So are there any qualities that C has to look at internally, or can you just be?
That's a fantastic question. So generically, no. Yeah, in fact, C can be negative, right? And if you think about it, no matter this is actually a common misconception. This is a linear program in the sense that my variable here is pi. C is a constant, right? And all the constraints I have are linear inequalities, right? So like even if C is negative and weird and satisfies no properties at all, this thing is still solvable. It's still like polynomial time and well behaved. Is it distance? No. Then you need more properties on C. But like this is a perfectly well posed problem for a huge class of functions C. In fact, you can even imagine like binary ones. Like maybe I pay nothing if I move 10 feet, and then I pay everything if I move it more than 10 feet. There's a lot of different models you can put here. In fact, there's some really interesting machine learning papers that try to reverse engineer C given like pairs of measures or something like that, or like an economics problem. Cool. So to add to Zoe's question, we can put more structure on the function C. So for example, maybe we think of it as geodesic distance to the pth power. So when p is equal to 1, think about it as like mass times distance. It's kind of like work. When p is equal to 2, it actually kind of corresponds to kinetic energy. We'll come back to that a little later. But generically speaking, I can define the following quantity, which is I solve the optimization problem from the previous slide, and I take it to the 1 over p power. Notice that I could have moved the min inside the parentheses here. That doesn't do anything. And this thing has a name. It is called the Wasserstein distance. Ironically, this was not proposed or even really analyzed a whole lot by Wasserstein, but such is history, and now we have it. Actually, there was one effort to try and change it to the Kantorovich distance, and it never took. But in any event, this thing satisfies a triangle inequality on the space of probability measured. This is a distance in a very abstract space. Do we see that? So to go back to Zoe's question, like generically the problem is well posed for any choice of C. When you choose C to be distance, then this quantity kind of becomes a distance on the spaces of mu's and nu's, right? And so that's why a lot of time when you hear people talk about transport problem, they talk about like, WP is sort of a mechanism for mapping distance functions on a base domain, like geodesic distance, to distance functions on probability measures, right? It's like somehow lifting. Any questions so far? A weird noise in this classroom. Okay. Right, so let's go through a few special cases of this thing, just to kind of see what it looks like. So here's a very simple one-dimensional one. So here I'm in 1D, so now my cost is just like x minus y, the absolute value like that. And even there, you can set up computational experiments with this easily enough if you play with it. One thing that you'll notice is that pi ends up being really, really pointy. So like in general, like pi, so this is a typical visualization. You can only do this in 1D. So like I have rho naught and rho 1. And remember there's a pi of x comma y. So like for every pair of points you get a variable. So like these are 1D distributions. You get kind of a 2D function on the right-hand side. So here like I made this figure so I can tell you. I just optimized for this big square worth of numbers. And notice what happened. Like pi has all of its interesting values on this little tiny thin slice of space, and everything else is 0. A priori, that doesn't have to happen, right? Like we don't know that from pi of xy. Could be, for example, that pi of xy is just rho naught times rho 1, like rho naught of x times rho 1 of y. You'll see that satisfies constraints. So this empirical observation is actually a very, very deep theorem. This is I think called Brennius theorem. And essentially what it says is that under pretty mild assumptions on rho naught and rho 1, like that they're absolutely continuous, which means they have a density function, so they're not like deltas. Then the transport plan here really is concentrated on like a little graph. Like there's a function that maps x's to y's that is telling me where to move all of my mass. Do you see that in this picture here? Like if I go horizontally, there's only one place where this is non-zero. A different way of putting that is that like I never need to split mass in half, right? This is a very, very deep theorem, and it's not one that we will prove in this class. However, Brennius theorem actually resolves a math problem that was left over from Monge in like the 1700s, right? Like because originally the way that the transport problem was posed was not in this integral formulation, but rather find me the map that pushes forward rho naught onto rho 1. And the reality is it's not a well-posed problem unless you put some assumptions on rho naught and rho 1, which is why it was so hard for Monge to prove anything, because it wasn't true. In one dimension, incidentally, there are closed form formulas for this, so like you don't have to solve this program at all. In fact, here's a little handy thing you can do. So W1, remember the difference between W1 and W2 is whether cost is squared. W1 is nothing more than the L1 distance between cumulative distribution function. Remember that's like the integral of probability density. W2 is the difference, the L2 difference between quantile functions, which is inverse CDF. This is a fun fact kind of thing here. In fact, if you want to do W1, it's very simple. If you have two samples, you just sort them and then you take the distance, like between sorted vectors. So to do a few more special cases here, let's say that our two probability measures are just a bunch of like a combination of little delta functions, so they're just concentrated at isolated points. Well, now that function pi of x comma y is pretty much 0 everywhere except for pairs of points where there's like little piles of mass, right? So if you think about it, this program ends up kind of reducing to a linear program, right? So here now a naught and a1 is like, a naught I is like the amount of mass that is piled up at point I in a naught. Similarly for j. Then notice that this is nothing more than just like a discrete version of what was on the previous slide. That makes sense? So this is like the picture you should have in mind. Like now, rather than like this nice smooth function with piles of sand, I've got these discrete points. And notice this is a linear program. And because again, the variable here is t. It's not the x's or the a's. Right, so in fact, this is a very well-known linear program. It's called the transport linear program. There's actually an analogy of Brennius theorem in this case, which is much, much easier to prove. If you go take a linear programming course, you'll probably learn about what they call total unimodularity, which says roughly, it implies that T has to have order n non-zeros, even though it's an n squared matrix. Which is, if you think about it, like kind of some version of Brenier, right? Like it's saying there's like a linear number of places where I can move mass around. There's one more kind of interesting case, and then maybe we'll stop for today and we'll continue. We'll do two more interesting cases, and then continue next time. And that's something that I think unless you're in optimal transport theory, you really wouldn't think about a whole lot. But it turns out to be really important from a computational perspective. And was actually one of the very first ones to be studied in the geometry community, which is something called semi-discrete optimal transport. So in the fully discrete case, right, we have two different little piles of delta measures, and now our program, this is obviously solvable. Like you guys have been playing with CVX all semester, and you could easily implement this model here. In semi-discrete transport, I take one of my two input measures, and I say that one of these two guys is discrete, but the other one is anything at all. So like you see this schematic here. So like here I've got a few isolated points for the red measure, but the blue one is some smooth function. And we'll see a more generic version of this later in this lecture. Here's just the 1D1 to get you kind of thinking about why this might be a tractable problem to solve. Because like initially it doesn't feel like this should be any easier than like the totally generic case, right? Right. But here's the way to think about it. Let's say that I have these two adjacent red points of mass here. And for some reason, when they map into the blue distribution, they flip ordering. Right? So like the right guy moves to the left of the target of the left guy. Did that sentence parse? One thing you can easily argue is that if you swap those two targets, your transport cost will decrease. Does that make sense? And like I think at least intuitively, like that kind of feels right. If you get us a scrap paper, you can check that. Like, yeah, that has to be the case. So as a kind of a byproduct of that argument, you can actually solve this problem in kind of a sneaky fashion, which is that if you think about it, what that implies is that all of the mass assigned to the first guy has to be the left of all the mass assigned to the second guy, which has to be the left of all the mass assigned to the third guy, and so on. Yeah? So in the reality, what I'm doing is I'm computing a partition of the blue distribution. You see that where the first chunk of it is all assigned to the first guy, the second chunk of it is all assigned to the second guy, and so on. So in fact, even though it doesn't feel like it, there's actually a finite number of optimization variables in this problem. Right? Like the function pi that we defined before is not finite, it's infinite. But here, secretly, I can just look for the dividing lines between these cells. So there's some weird change of variables here that makes this into a finite problem. And what we'll see is that the intuition in 1D is quite simple. It's very easy to draw a picture of this. In higher dimensions, actually, the intuition carries through. And what you end up computing is some analogy of a Voronoi diagram. So I think it's a very familiar object in computer science class. The problem with Voronoi cells is that you don't have control over their size. Like they could be big or small. So it's not quite a Voronoi cell here, but it's something called a power diagram where you get to kind of control how big or small the cells in your Voronoi diagram are. So there's actually a really nice link between optimal transport and the semi-discrete area and like computer science theory and algorithms people that study like how to do very fast computational geometry. These are linked together in a nice way. One additional formulation of this problem, and maybe we'll stop for the day, is actually the original one to be proposed in the theory of optimal transport. The only issue is that it's not always solvable, which is why Monge kind of struggled with it. Which is originally Monge thought like, oh, I should just be able to find a target for every point t, so I'm going to optimize this form of this problem where I just look over all possible maps from source to target and find the one that kind of warps one distribution onto the other. The reason why Monge wasn't able to solve this problem is if I do this in generality, let's say that this is rho naught, it's just a delta function at a point, and then rho 1 is a delta function at 2 points, then obviously there does not exist a single map from rho naught onto rho 1 that covers the rho 1 distribution, right? And so like this problem is sort of ill-posed unless you put some additional structure on your probability distribution. And so essentially what Brenier showed is that so long as one of these two guys has a density function, this problem can't happen. It might not be a nice map, it could be discontinuous and weird, but it exists. Okay? So that was sort of the resolution of this problem, and it took like, 200-300 years to get there. Okay, so maybe we are now experts in the formulation of the optimal transport problem. We're about at the end of class. So when we continue next time, what we're going to see, like so far we've already seen about 3 different formulas for the same quantity. And we'll see that the transport problem is really weird because like every community has tackled it, but they didn't realize it until after, and they all end up with completely different formulas. So for instance, statistical physics, they've linked it to like random variables and these things like Brownian bridges. In fluid dynamics, it turns out that you can interpret all of this stuff as sort of a density of a gas changing over time. And there are all kinds of equivalent things that all lead to the same measurement. And then the really weird thing computationally is that depending on your setting, you might want to borrow one of these formulas or the other to get an efficient algorithm. This is a space where there's not consensus. Okay, so with that, maybe we'll take a break. Hopefully this language is sort of okay with you since you all did that transport problem on your homework anyway. And we'll pick it up on Tuesday to talk about how to actually solve these things in practice. Good luck if you're finishing your homework. Okay, so now I do 3, 2, 1.